Welcome everybody. This is section 2.5, limits at infinity. Let me highlight that. So what does that mean? We're going to start off with the definition. It's a definition of a horizontal asymptote. We've already done the vertical asymptote. You should know and understand the definition of the vertical asymptote. Now this is the definition of a horizontal asymptote, and you shouldn't memorize this. This should make sense logically. So I'm going to draw a graph down here. I should have left myself more space, but I think we'll get the idea. So conceptually, what's happening here? What is this definition saying? You shouldn't, again, have to memorize this formula or this definition. It should logically make sense to you. So I'm going to label this L and this M here. So let's look over this and think about what this is actually saying. Let's look at the first one. Let's see if I get my mouse working here. There we go. This one here. So this statement here, x going to infinity. In your head, you should see yourself moving far to the right. So the limit is x goes to infinity. As I move to the right, what's happening? The next thing you should see is this. The function, or the y value of the function, gets really close to or equals what? It gets close to or equals L. So visually, what you should be seeing on the graph, this part here saying as I move to the right, the function gets close to or equals L. So that becomes a horizontal asymptote to the right. So I'm going to do a dashed line to the right. And here's the part. You don't know how it's going to approach that line. You just know it's approaching it. So the way you draw it can be a lot of different ways. I'll give you a couple examples. One way could be this. It could look like this. And that would be a horizontal asymptote because it follows this. As I move to the right, the y value of the function gets closer and closer and closer to L or equals L. So that's one possible solution. Now, a lot of you have this assumption in your head that you can never cross an asymptote. You can never cross a vertical asymptote, but you can cross a horizontal asymptote. Let me give you another example of a function that fits this definition. So what if your function looked like this? Okay, let's see if it fits. This is saying as I move to the right, the y value of the function gets closer and closer to L. That is true. As I move right, the function gets closer and closer and closer and closer to L. So those both fit the definition. So you got to get out of your head that thought that you cannot cross an asymptote. You cannot cross a vertical, but you can cross a horizontal asymptote. And there's your example. Okay, so we're going to look at the same thing, but on the left side. So if you look at this here, the only difference is you're moving to the left. It says as you're moving to the left, this is saying your function f of x, or your y value of your function, does what? It gets really, really close to m. So it's the same thing, but now we're moving to the left. So here's m down here, and to the left, we're going to have a horizontal asymptote to the left. Now my function does not necessarily have to connect to the function on the right. It just has to pass the vertical line test. But I'm just going to make mine connect, and it could do this and do that. So that is an example of how the definition of the horizontal asymptote works. You should not memorize those. It should be a visual picture in your head and it makes sense, just like the vertical asymptotes. You should have a visual picture of why the definition of the vertical asymptotes are the way they are. You need to know those. Those will appear in multiple choice questions where they'll give you the definition and you'll have to recognize, oh, that is a horizontal asymptote or that's a vertical. So make sure you understand those. Again, I'm going to emphasize all year long, don't memorize, understand. So the rest of this section is going to be how to find what's called limits at infinity. Both of these, x goes to infinity, x goes to negative infinity, these are examples of limits at infinity. And so you have to be able to find those limits. We haven't done those yet. So we're going to look at those. But before we do that, we are going to do a conceptual thing here. You probably should pause this and see if you can draw this. So go ahead and pause. I am going to do this problem for you. Okay, hopefully you were able to graph that. Now I am going to take the given points. F of 0 is 4, so I'm just going to put a point there. F of 2 is negative 4. I'm just going to put a point there. So I've taken care of those two. And f of negative 2 is negative 1. And I'm going to put a point there. Now, what do these other four limit statements tell me? This is what you have to recognize. So they're all asymptote statements that you need to recognize as asymptotes. The first one here, this says, as I move to the left, the function gets really close to 3. You should recognize that's a horizontal asymptote to the left of 3. So I'm going to draw a dashed line to the left, indicating that's my horizontal asymptote to the left. Now this statement here, this says as I move to the right, the function gets really close to negative 1. So to the right, I'm going to draw a horizontal asymptote at negative 1. So we've taken care of those two statements. Now, this is the one here you have to recognize. It shouldn't be a memorized thing. It should make sense. This says as I get close to 3 from the left, the function shoots up. The y value goes to infinity. So that means at 3, I have a vertical asymptote. And not only do I have a vertical asymptote, from the left, the function goes up. And then this one here, as I approach from the right, the function goes down. So the way the function looks is a guess. That's why it says a possible graph, because it could do many things. I'll give you one example. This could just simply do that, and that would work. Or if you want to go crazy, let's go crazy. It could actually look like this, like I did before. That's a possibility. Or it could do this. So there's a lot of possible answers. I like just doing just a very basic intuitive and just do nice curves. Now I have to come down here. I have to go through those 3 points. So I'm just going to make those like vertices. And just approach like that. Now, as long as you go through those 3 points, and as you move to the left, you approach that horizontal asymptote, that's fine. That's not the only answer. Again, there's a lot of them. So that gives you an idea of conceptually horizontal and vertical asymptotes that you have to understand and how you would draw graphs. Let's continue on. So the next concept is, how do you find limits at infinity? So I want to do an example, and hopefully this makes sense for you. We are going to find the limit as x goes to infinity of 1 over x. And the way we're going to do this is we're going to make a data table, and we're going to kind of see intuitively what's happening, and then I'll give you the concept of what you should understand. Okay? So let's do this. Make a data table. We'll start at 10, and x gets larger and larger. Uh-oh, I'm going to run out of room here. Okay, so first plug in 10. 1 divided by 10 is 0.1. Divide by 100. I'm just going to go ahead and fill this up. If you don't believe me, you can double check on your calculator. Now the question is, what happens to the y values as I continue moving right? I hope it's clear to you that they're approaching 0. So here is your basic concept. If you have any constant divided by a number that's going to infinity, that limit will be 0. Any constant over a number going to infinity, that number will be 0. So another way to think about this, the top number tells you how many you have. Oops, oh, I didn't want to do that. The top number tells you how many you have. I have 1 pizza. The bottom number tells you how many people are splitting that 1 pizza. If I have 1 pizza and I split it with 1 person, I'm happy because I get a whole pizza. If I have 1 pizza and I split it between 2 people, I'm still pretty happy. I like a half a pizza. And even split between 4, not bad. I get 1/4 of the pizza. But as x gets larger and larger, let's say x is 100. If I take 1 pizza and split between 100 people, I'm very sad. Here's me. Because you chop a pizza into 100 slices, you're not getting much at all. Imagine you take 1 pizza and split it between 1,000 people. Wow, you're getting like a crumb of a crumb. And now you're even bigger sad because you're not getting anything. So conceptually, that's what's happening. You have to recognize this quickly. A constant over infinity approaches 0. And even you might say, but what if we start with a lot of pizzas? Yeah. What if we start with 1,000,000 pizzas? It's still going to go to 0 because the bottom x is going to infinity. So when x is 100 million and you have 1,000,000 pizzas, each pizza is split in between 100 people. And then you have 1,000 million, known as a trillion, 1,000 million. Each of your 1,000,000 pizzas is being split between 1,000 people. You get 1/1000th of a pizza. So no matter how big your numerator is, if it's a constant and the bottom's going to infinity, the size of your pizza is rapidly approaching 0. So that's the concept you have to understand. Constant divided by infinity approaches 0. And not just that, if it doesn't necessarily have to be a constant, it has to be a bound number on top. If like I have a number on top that's fluctuating between 0 and 1, let me go ahead and show you that. Now the top is not a constant. As x goes to infinity, sign changes. But the top The biggest sign could be is 1. If you remember the sign function, the small sign could be is -1. So the top numbers between 1 pizza and -1 pizzas, or somewhere between that. And if you split that between more and more people, clearly it's going to go to 0. So if the top number is bounded, we're going to get 0. And as we go on, you will learn more examples of 0, even if the top is not a constant. But for now, I think we're good. So I'm going to put a couple examples. You can pause and try it and see if you did it correctly. Okay. Here's going to be your first one for you to try. Actually, I'm going to put 2 down. After I put these 2 down, you can go ahead and try to do these yourself. Here's the other one. And as we do these, I just want to remind you, please don't memorize. Make sure it makes sense why the answers come out. You're not just memorizing some formulas I gave you like the ones above. So go ahead and pause. Try these. Rightio, everybody. Hopefully you had some success. If not, hopefully you learn from these. So technically, I need to split the first one into 2 separate limits. You don't have to. I'm going to do that using, just to do it properly. All right, so we already know this. This is a constant function. It always equals 2. So no matter where x is going, that function will always be 2. The next one, you have 10 pizzas, split between an infinite number of people squared. Clearly that's 0. So hopefully you got 2 for your answer there. All right. The next example, split it into 2 separates. All right, 3 is a constant here. So the function always equals 3. So no matter where you are, the function is 3. Now as we look at the next one, the top is bounded between +3 and -3. So conceptually, like 3 pizzas to -3 pizzas, you have somewhere in that range. The bottom is square root of infinity. Well, the square root of infinity is still going to be infinity. So you have a maximum of 3 pizzas split between an infinite number of people. Clearly, again, you're going to have 0, oopsies, 0 there. And that limit is also going to be 3. All right. So that's that one. Let's go ahead. Okay, yeah, let's start getting into the gist of this stuff. So more stuff happens. Not only do you have horizontal asymptotes left and right, you have infinite limits. So a limit at infinity can be a limit of infinity. And we're going to see those. And graphically, you need to understand what that means, what that looks like. So I'm just going to do, I think the best way to do this is to do examples and then give you kind of what the graph looks like, which some of these you already know. So let's do this example. The limit as x goes to infinity of x squared and the limit as x goes to -infinity of x squared. Okay, so here you think to yourself, well, if I get infinity squared, that's going to be infinity. And if I get infinity squared, even if it's negative, it's going to be infinity. So graphically, what does that look like? You already know what this looks like. It's a parabola, right? So let me graph your parabola, and then we will connect that with the meaning of this graph. So let's look at the first one here. What is this saying here? As I move where? To the right. The function, the y value of x squared does what? It goes to infinity. And look, as I move to the right, the function goes to infinity. So you should recognize if you have a limit at infinity and it goes to infinity, the function's going to move upwards without bound. And similarly, let's look at the other one. This says, as I move to the left, the y value of the function goes to infinity. As I move to the left, the y value is going to go up. So that's how that works. So that gives you an idea. So again, technically a limit, if it keeps getting bigger, the limit technically doesn't exist because it's not approaching a number. It's not getting really close to a number. But when we put infinity, it's to tell us that it grows without bound, and graphically, the graph goes up at that point. So that's what's happening. This is kind of like a vertical asymptote, but instead of approaching a vertical line, it just keeps getting bigger as it drifts right or left. All right, I'm going to do a couple of examples for you and explain to you how to do this, and we'll do more, a few more, just more examples of strange end behavior. So horizontal asymptotes is known as end behavior. So when you have a horizontal asymptote, that's the behavior at the ends of the graph. The previous example of the parabola is also end behavior. What happens as x goes to positive infinity and negative infinity? Well, in this example we just did, we have infinity on both sides. So I'm going to sneeze. Hold on. Ooh, sorry about that. So it tells you what happens at the end. As I move to the right, the end goes up. As I move to the left, the end goes up. These are all end behaviors. So limits at infinity teach you end behavior of a graph. What happens as you move right and what happens as you move left. So that's what's happening. Let's do an example here. Not what I wanted. So we have this function. And we want to know the end behavior. So we would do the limit as x goes to infinity of the function to find the right end behavior. Well, how do you do this? Because there's so many things going on there. So here is your general rule. And you got to be careful with these rules because you will use these rules in places where you're not supposed to use them. And I'll give you the example. But when x is going to infinity, like it is here, the lower powers, the second power and the first power and the no power, the zero power basically, you have x to the zero there, those become insignificant compared to the highest power. So all you have to do is look at the highest power, because I'll just look at x to the fourth and x squared. If x were 10, 10 to the fourth is 10,000, 10 squared is 100, right? So this would be 100 times bigger than that. Now if you make x 1,000, you would have how many zeros? I mean, excuse me, x 100, I haven't done 100 yet, or have I? I am so lost in my head. 1,000. If I had 1,000, I would have, what, 12 zeros? And here, 1,000, I'd have 6 zeros. So this is now 1,000,000 times bigger than that. And x gets larger, this grows, this will be an infinitely larger than that. And if something's infinitely larger, this is insignificant. That's why we can ignore all the lower powers as x goes to infinity. So if you look at that clearly, 3 times infinity to the 4th is infinity. So what does that tell you? As I move to the right, the graph moves upwards. And you know x to the 4th is like a parabola, but steeper, right? So that makes sense. Now here is where the danger lies, is where you start to memorize things and not really understand what's happening. If I were to give you a problem like this, and you say, oh, I can ignore all the lower powers. That equals 3 times 1 to the 4th. That's going to be 3. And that's not correct. The only reason you ignore the lower powers when x was going to infinity is because 3x to the 4th became infinitely larger than the rest of the terms. Therefore, the rest of the terms became insignificant. In this case, that's not true. If you plug in 1 into all the x's like you're supposed to do, you would get a completely different limit. So be careful. Don't assume. Don't apply rules in situations where they don't apply. That's just a warning to you, the dangers of memorizing. And you might say, I would never do that. That's so obvious. But there are other cases where it's not so obvious and you start applying rules you shouldn't. All right, let's do one more example. You can try it, and then we will move on to some more difficult situations. All right, find the end behavior. Oh, and the previous one. Let me show you the previous one. I didn't find the left end behavior, so I should have done that. So let me do that real quick before you pause this. So again, when you have a polynomial and an infinite limit, you can ignore the lower powers. So that's going to be 3 times negative infinity to the 4th. But a negative infinity to the 4th is a positive, so it's just going to be positive infinity. So that just tells you left and right, it's going to be going up. In between, other things may happen, but as I move right, it goes up, and as I move left, it goes up. So that's what that tells you. And if you do that a couple more times, you get a spider or a crab, or you get something. All right, let's move on. Find the end behavior of this polynomial. Go ahead and try it. And you can unpause after you're finished and see what it comes out to be. All right, so we'll do the left end behavior first. The limit as x goes to negative infinity of p of x. Since we're going to infinity, all the lower powers are insignificant, so we have negative 2x cubed. So negative 2 times negative infinity cubed will be negative 2 times negative infinity, right? That's going to get us positive infinity because the negative and negative get you positive. Hopefully you got that. And then the limit as I move to the right, or positive infinity, of our function, we ignore all lower powers, it'll be negative 2 times positive infinity, right? Well, that's going to be negative infinity. Now, a side note, you should not be writing this down. I just do that so you kind of see what's going on in my head, but you shouldn't write that. You just put your final answer. All right, more examples. So now you should know that limits at infinity give you end behavior. Now you have to know how to find limits of infinity. We've done it for polynomials. We've done it for a constant over infinity. Now we're going to do it for rational functions. And then after that, we have even a crazier example. And and then we have to review some logs and exponential functions. So we have quite a bit more to go. Hopefully this doesn't become another hour video, but I fear it might be. We'll see what's happening. All right, more examples. This first one, you probably should just watch what I do, and then the other ones you can try yourself. We want to find the right end behavior and the left end. So sad. We got to do both sides, but we can do that pretty easy. This is called a rational function. A rational function is a polynomial function divided by another polynomial. Now, we're not going to use any shortcuts at first. The top is 3 times infinity plus 2. The bottom is infinity squared minus 1. And I will give you some shortcut stuff at the end. But if you look at that, you're like, uh-oh. I don't know. I don't know what to do. So the secret to solving this, here's the problem. You have 0 over 0. No, sorry. Liar, liar, pants fire. Infinity over infinity. Infinity over infinity is like 0 over 0. It's indeterminate. You cannot tell. Infinity over infinity is not 1 because all infinities are not the same. So that's part of our problem. So the secret is to get the bottom to not be infinity. To get the bottom to not be infinity, I could do that dividing by x squared. So I'm going to multiply by 1. We like multiplying by 1. But our 1 is going to be special. It's special because our 1 is going to be x to the power of the denominator. The power of the denominator, or the degree of the denominator, is 2. So we want to divide the top and bottom by x squared. Because the degree of the denominator is 2. So I want to divide top and bottom by x squared. So we just distribute these. And nice things happen, hopefully. Limit x goes to infinity. So let's do 1 by 1. I probably shouldn't have. Okay, yeah. Let me do different colors for you guys. That 3x divided by x squared is 1 over x. And then another color. Distribute that. That becomes 2 over x squared. Do blue. Do that. That becomes 1. And let's do another beautiful brown. Minus 1 over x squared. Now let's go to the next step. All right. What does 1 over infinity approach? 0, because we have a constant over infinity. 1 pizza divided by infinite number of people. 2 divided by infinity squared. 2 pizzas split up between infinite number of people. You get no pizza. 1 minus 0 again. You get 0 over 1. So that is 0. So that is happening to the right. There's a horizontal asymptote at 0. That's what you should be seeing. All right, let's keep going here. We have to find out what's happening to the left. I'm going to show you, if I do a negative infinity, it doesn't change anything. If I do negative there, negative there, negative there, it's all the same. So to the left and to the right, the horizontal asymptote's at 0. So you're going to apply the same rule I just gave you to the next 2 examples. So I will write the examples down, and then you can pause and try it yourself. So the next one, you can go ahead and copy this and try it yourself. The negative infinity, you're going to see that it's going to be the same. Whoops, that's a minus. So use the technique I used previously on that example. And then the third example, and you could either work one at a time or work both of these first. It might be better one at a time, but I'll just give it to you. Third example is going to be this one, x cubed minus 2x plus 1 over 2x plus 4. I will work these out, so you can do one at a time or both. So give it a shot. All right, we'll do example 2 first. So hopefully you recognize you have to multiply by 1. The secret, divide top and bottom by the degree of the denominator. It's 4. So my 1 will be 1 over x to the 4th divided by 1 over x to the 4th. So this will equal, so first we'll do these two. Wow. That will get us 10. I'm going to run out of colors here. There's too much going on. Now I'll do these two. That's going to be minus 4 over x squared. Wow, that's hard to see. And we'll do the orange one, these one. 1 over x to the 4th. And then I'll do red. We'll distribute that. That'll get us 10. Then that beautiful color. That will get us 8 over x squared. And then green. 1 over x to the 4th. And this becomes pretty easy. So 10 is 10. 4 over x squared, that's going to be 0. 1 over x to the 4th, that's 0. Again, the principle, you have a constant number of pizzas split between an infinite number of people. No pizza for you. So our answer is going to be 1. All right? Here's the next one. The degree of the denominator is 1. So I want to divide both top and bottom by x. And I shall do 1 over x, 1 over x. So I'm going to go a little faster here and I'll draw all the arrows for you. Hopefully you're getting better with that. The limit of x goes to infinity. X cubed divided by x is x squared. 2x divided by x is 2. And 1 divided by x is that. On the bottom, 2x times 1 over x is 2, and 4 times 1 over x is 4 over x. So what happens here? Well, x squared is infinity squared. And 1 over x is 0. And 4 over x approaches 0. So I have infinity minus 2 over 2. Now think about that. If you have an infinite number of things, you take away 2, it doesn't affect it. You still have infinity. And infinity divided by 2, if you have an unlimited supply of something and you split in half, you still have unlimited supply. So clearly that's infinity. So that's the third example of when you have a rational function. So the first one tells you here, as I move left and as I move right, either way, it approaches 0. So I have a horizontal asymptote of 0 to the right and left. That's what the first one said. The second one, and again, if you put a negative infinity in the second one, you'll get the same answer in this case. Not always, but you will in this one. This says, as I move to the right, it approaches 1. So I have a horizontal asymptote of 1 to the left and right. And on the third one, as I move to the right, I get infinity. That means it's going to go up as I move to the right. This one, when you do negative infinity, you'll still get positive, but be careful because these are the cases where you might not get the same thing left and right. Okay, so that's end behavior of rational functions. I have a couple more examples to go. Hang in here. Again, long video. The good news is we're going to spend a couple days on this section. Well, a couple days because we have the meet every period. So we'll have our regular and then meet every period. So we'll have a little bit extra time on this. All right, and hopefully the lessons will start getting shorter. These are just very long examples. Here is the crazy one. We're going to find the end behavior. Find the end behavior of, wow, you're not going to like this, 10x cubed minus 3x squared plus 8. That's not the bad part. This is the part you're not going to like. 25 x to the 6th plus x to the 4th plus 2. So we have to find out what's happening to the right and what's happening to the left. Woo, here we go. I need the limit as x goes to infinity of this monstrosity so the technique remains the same. You want to divide by the degree of the denominator. And we'll see how this gets tricky. And there's some nuances here that some of your brains are going to pop, but you can just keep rewinding and looking at it and trying to figure it out. But like I said, Wednesday is our all day, every class, and so that'll be one extra day to kind of look at things and kind of summarize what's going on. But let's take a look. The bottom is an x to the 6th without the square root. So you have a 6th power, but when you square root x to the 6th, it becomes x to the 3rd. So our magic number we want to divide by is 1 over x cubed. That's our 1 that we want to multiply by. All right, let's take a look and see what happens. The limit as x goes to infinity. Now distribute that 1 over x cubed here. You would get 10 minus 3 over x plus 8 over x cubed. Now the bottom is where it becomes interesting. And here's where I want to do some side work and show you something. Now, here is the gist of the problem. We have a square root here. This is not a square root. Something is square rooted, you can't divide it by something that's not square rooted. That's a problem. If this were a square root, that would be no problem. So what we're going to do is convert and recognize x cubed is the square root of x to the 6th. You have to recognize these are equivalent. So what I'm going to do is change this to square root of x to the 6th. So now, when I divide by square root of x to the 6th, that's what's happening. Now I'm allowed to divide that because they're both underneath the square root. So that's just a way of rewriting to get them all underneath the square root sign. So we divide the first ones. The x to the 6th is canceled, leaving 25. We do the x to the 4th divided by x to the 6th. We get 1 over x squared. And the 2 over x to the 6th, clearly we get 2 over x to the 6th. Now we take the limit. As you can see, if we have a constant number of pizzas divided by infinite people, that goes to 0, that goes to 0, that goes to 0, that goes to 0, because we're splitting our pizza with infinite number of people. What we're left with on top is a 10, and on the bottom, square root of 25, so 10 over 5, 2. So what did we learn? There's a horizontal asymptote to the right of 2. Cool. Okay, I'm going to attempt to do all of this again with a negative going to the left. So I'm going to try to copy all of this and change something really small. Bam. Can I copy that? I'm not sure what I'm doing, guys. Yes, copy. And I want to paste it down here. Oh, that's small. No bueno. Yeah, there we go. Let's move it down here. So the only difference is this. I want to have a negative infinity. I want a negative infinity. Well, not a whole lot changes except, yeah, this is where it gets weird. This guy over here, that is only true when, okay, I gotta explain this to you. I gotta do some side work here. If I have x cubed, I take the limit as x goes to infinity. This goes to what? Infinity, right? Now, yeah, sorry. If I do the limit as x goes to negative infinity of x cubed, that will be negative infinity. Just a reminder, right? So just have that in your brain. I'm going to erase that. Well, what's happening special here is I have x going to negative infinity. Let's take a look at this statement right here. What happens if I put negative infinity for x? So I will do that down here and show you what's going on. If I do negative infinity to the sixth, excuse me, that's going to be infinity to the sixth. That's going to be in square root of infinity to the sixth, infinity to the third. It's going to be infinity. So even though I plugged in a negative infinity, that gets me infinity. We have a problem. We want to be going to negative infinity, not infinity. So here's the thing. If you put a negative infinity here, you will get positive infinity. But if you put a negative infinity here, you would get negative infinity. These two do not equal each other. They do not. We have an error. So this one, if we were to plug in the values, we would get infinity cubed. Infinity cubed, well, that's just infinity. Oh, sorry. Negative infinity cubed, because we're doing negative now. Liar, liar, pants on fire. We have an untrue statement. So it's not true that x cubed equals square root of x to the sixth when x is negative. That statement's only true when x is positive. But now I'm doing x is negative. So how do I make that statement true? I'm dividing by x cubed. Let me erase all this again. Well, I don't know why it's not erasing. I'm sad. Oh, because it's a copy. Oh, that's so bad. But watch this. I'll copy over it with white ink. Ah, you can't see it anymore. Kinda. Yeah. Okay. Now copy over that with blue. I cannot replace x cubed with square root of x to the sixth because as we see here, they're not the same. As x goes to negative infinity, they're not. So in order to get them to be the same, when x is negative, I need to put a minus there. That puts a minus there, a minus there, a minus there, a minus there, and now it's a true statement. So I know that that's kind of hard to see. If you want to come in for our extra sessions, I can go over that with you. Honestly, that rarely appears on an AP test, but it's good for you to exercise your brain and to kind of grasp the concepts that's going on here. But now when x is negative infinity, I replace this with 1 over negative square root of x to the 6th. So I need a negative there. And what that's going to do, that negative is going to stay on the outside because only the square root part gets divided in here. That negative stays outside. That becomes negative, and my answer is -2. So as I move to the left, it approaches -2. Hopefully you followed that. All right, you're going to have some of those to do as homework. The main thing, I'm not going to give you one of these. I would rather you just kind of look through this example and try to understand why I put the negative there and make sure that makes sense. But that's what you're going to be doing in some of your homework on the next night. Okay? So we're not done. I'm sorry again. I think this is another really long video. But you have time to go over it. You have time. You have a day off, so this is like 2 lessons and for 2 days, so it's normal. All right, end behavior. We have some functions that you have to know the end behavior for. These functions actually are essential. They're used all the time in calculus. So I'm going to draw them for you. Actually, let me do this in Desmos for you. You need to know what they look like. I'm going to point out some things about them. So let me go to Desmos. Where are my calculators? There they are. Bam-o. Wham-o. Okay. Very important function you have to know. E to the x. E to the x. There's got to be a faster way. There is e to the x. Bam. So, things you have to know about e to the x. Exponential function, it goes through 0, 1. Maybe I'll screenshot this and then annotate that. Okay. You have to recognize, must. Always goes through 0, 1. Then, you should notice over here, it has a horizontal asymptote of the x-axis, and it goes up. Have to know that. So this is y equals e to the x. Have to know that's what the function looks like. And so if we want to take limits here and find end behavior without even knowing, well, you should kind of memorize this graph. I tell you not to memorize. There's some things you have to memorize. The limit as x goes to infinity of e to the x is infinity. So as you move to the right, the function gets increasingly large, and you can see it moves up over here. So that's the right end behavior. Excuse me. And the other way to think about this, you have to realize e is just a number. It's about 2.714. So when you see e, it's not a variable in the sense of it's not changing. It's a constant. E represents a constant. 2.714, blah, blah, blah. It goes on forever, just like pi, but just a different number. So if you take 2.7 and raise it to the infinite power, clearly that's going to infinity. So logically, without the graph, you should know that. And then, let's do this. The limit as x goes to negative infinity of e to the x equals. And if you look at this graph, if I move to the left, clearly it's going to 0. But how would you do that without a graph? Suppose you don't know that graph. Here's what you would do. You would say e to the negative infinity. Well, if I have a negative exponent, I know that I flip it, and it becomes a positive exponent. So 1 over infinity clearly is going to 0. One pizza split between an infinite number of people. So that's 0. So that's one graph you have to know. And then let's do a next one. Can I delete that? Yeah, we'll delete that. What if you have a negative exponent here? Where is my negative? Is minus and negative the same in Desmos? We'll find out. Yes. Okay, let me screenshot this. And then we will. Wow, when I tried to screenshot it, I didn't hit all three buttons at the same time. I turned it off and my recording stopped. So let's try it again. All right, so this is y equals e to the minus x. So what's happening here? Well, when you put a minus on your x, you reflect it over the y-axis. So it's the same as e to the x, but reflected over the y-axis. So now you have a horizontal asymptote to the right, and it goes infinity to the left. So that's what's happening here. So you have to understand the end behavior of that. So if we do the limit as x goes to infinity of e to the minus x, you should know by looking at this, it should be 0. Or another way to look at this is the limit as x goes to infinity of when I have negative exponent, you need to know that that's 1 over e to the x, and it becomes a positive, and that becomes 1 over infinity, which is 0. So that's a right side end behavior. And the limit as x goes to infinity, negative infinity, oh, Yoshida. Whoa, what are you doing? Negative infinity of e to the minus x. So if you plug in negative, you have e to the minus negative infinity, which is e to the infinity, which is infinity. So as you move to the left, it goes up. So that's e to the minus x. Let's do one more end behavior. And hopefully I don't stop the video this time, or recording. ln. This is used all the time. You have to know what the ln function looks like. You just have to. And there it is. It is the inverse of e to the x. So all the x and y values switch. So let me screenshot this. Hopefully I don't turn it off. Okay, I succeeded. So remember e to the x, what it looked like? It went through that point, and it kind of looked like that-ish. So all x and y values are switched for the inverse. So instead of going through 0, 1, it goes through 1, 0. Instead of the negative x-axis being the asymptote, the negative y-axis is the asymptote. So you can kind of see it's just also the other way to do inverse functions, you reflect it over the line y equals x. So that's what's happened. So this is the function. I guess I can erase some of this stuff. This is the function ln x. You have to know what that looks like. It is used all the time, and it's assumed you know what it looks like and some common values, and we'll spend more time on this. But if you take the limit as x goes to infinity of ln of x, well, it's just going to go to infinity. ln's of bigger and bigger numbers gets bigger and bigger, and that's bared out by this graph continuing to increase. Now the other one, this is limit as x goes to negative infinity of ln of x. That does not exist because the graph doesn't exist at negatives. So that's not going to be one that you see. But you will see this, the limit as x approaches 0 from the right of ln of x. As you approach 0 from the right, it keeps going down. That's negative infinity. Now, one for fun, limit as x approaches 0 from the left of ln of x. You can pause and think about this. The answer, the graph does not exist because it doesn't exist to the left of the y-axis. That is the end of the video. All right? Probably a long one again, but we'll get through this. Hang in there. I will talk to you guys later.